Okay, ladies and gentlemen, this is Ghulam Mustafa Abdo, and I'm a PhD student at Electrical and Electronic Engineering Department, University Technology Petronas. The paper that I have submitted and accepted is Performance Evaluation of Newton-Euler and Quaternion Mathematics-based dynamic models for an under-actuated unmanned aerial vehicle. So what do you mean by under-actuated system? Actually, it's a mechatronic system, and if the number of actuators and the degree of freedom is somehow misbalanced. Like, to be exactly, if I define under-actuated system is a system that has a more number of control, more number of um, the degree of freedom as compared to the number of actuators. So such system is known as the under-actuated system. And to be more precise, the object that we have been discussing in this particular presentation is a quadrotor, which is an unmanned aerial vehicle. And if you see, like, it has four BLDC motors, and it can move, in 6 degree of freedom. So again, the degree of freedom is greater as compared to the number of actuators. So this is an under actuated system. The main focus of this paper is, when I started doing research about this topic, is like I have gone through various research papers. Many of the people, they are focused on two types of dynamic models. Either they went for the Newton-Euler dynamic model, that is very common, and the second one is Quaternion mathematic based model, which is uh, proposed by some of the papers. So, why there was a need to study these two dynamic models? Why? Because when we discuss underactuated system, it's already unstabilized and more difficult to control. But when we include like unmodeled dynamic factors like wind disturbance or rotor efficiency, or maybe the payload disturbances or any other external disturbances, then this system is more complex and lead towards instability. So my aim was, or the paper, focuses on the dynamic models, that okay, what type of dynamic model that really consider these unmodeled dynamic factors within. So after evaluating that thing, the entire story is quoted in this paper. A person can, correlate the merits and demerits of both models. So Newton-Euler versus Quaternion model, there are several limitations of Newton-Euler as mentioned over here and cited as well in the paper, by the paper of 26, available in my conference paper. It's all because of, like, they have the singularity issue, and because of that singularity issue, our drone while flying will lose any orientation. This is one of the major concern. The second thing is, like, it has when we adopt the Newton dynamic model, over there we can see like sine cosine functions, and due to these sine and cosine functions, at every orientation we compute the sine and cosine functions. So it will take our time a lot, and due to this computation we will require a cost costly controller, or we require a cost if expensive hardware design. So these were the constraints with the Newton Euler. So what was the fix? Actually, the fix was very simple, and the fix was like, we can do various things, like we can uh, fix this thing within some bounded variations. Okay, these are the variations, and these variations we can uh, propose any robust control design or any other technique. But then again, if we talk about unmodeled dynamic factors in real, there are several things that cannot be ignored. Yeah, in terms of simulation we can do various things, but when it comes to hardware, it is more difficult. So keeping up in view, what type of technique, or there should be one technique through which we can adopt a model. So that was the idea behind all the things. So if we see the discrete cosine matrix, like if we do the work, the alternative solution, so it has again a problem, like a constraint of orthogonality. And if we consider like the bounded variations, again, if there are some more changes that are not lying into the particular bounded interval that we have mentioned, then again our drone will face somehow instability. Now, if we go and see all the techniques, then we are left with only one technique, that is Quaternion mathematics. So Quaternion mathematics is free from all such limitations, like they don't have any gimbal lock or singularity issue. The linearity of formulation is quite easy, and there is somehow the researcher is more comfortable with the algebraic structure. So the main idea of the paper is to present a performance evaluation of Newton, Euler, and Quaternion mathematics models, so that one can, propose an intelligent or hybrid control design or observer design by studying the simple mathematics of both models. So this is the summary of previous research contributions. You can see, like in this particular table, I have highlighted the 7 techniques, 7 per proposed algorithms, where most of the cases they have used Newton-Euler dynamic model. Only the 6th number has the Quaternion model, which is proposed by, with the backstepping control design with nonlinear reference model. So in this, the limitation that has been observed was there is a small steady state error, and when it comes to the payload variation. So this cause actually more steady state error if you just gradually increase the payload or decrease the payload. In addition to this, this is not only the 7 techniques, but yeah, we have the 15 techniques so far, and most of the cases people are using like Newton-Euler dynamic model rather than Quaternion model. Still, we can see that there are many constraints, like you can face the constraints of the gimbal lock. You can face the constraints of various things that are mentioned in this table. Like if we discuss like 14th one, though it proposes a fine controller, that is actually infinity controller, very powerful with a robust compensator design, but again if you see there is a chattering effect or Zeno effect. What do you mean by Zeno effect? Zeno effect is somehow the number of higher oscillations that deviates your quadrotor from a trajectory, like any trajectory, helical trajectory or circular or diamond shape. It deviates your quadrotor from the desired path, maybe from the desired target. So this is something that is really concern thing, that the main idea is not to propose a controller, but main objective is to study the dynamic model that really consider the unmodeled dynamic vectors. So if you can see the mathematical model, this is the quadrotor, and through this simple through mathematics you can derive the Newton-Euler model. Like there are 2 frames that is very famous, which are mostly used to demonstrate the motion of an unmanned aerial vehicle. The motion is planned via geographical mapping, thus one defines the earth frame of a reference or inertial frame. So we have like 2 frames, inertial frame and non-inertial frame. In the figure you can see the origin point of this frame of reference is labeled as EI, and which is a fixed point obviously, and one can visualize the linear positions like x by z of the quadrotor as well. uh, moreover, the non-inertial frame, commonly known as body fixed frame or non-inertial frame, is also highlighted in the figure 1. You can see over here like EB, the subscript B is actually the body fixed frame. So after driving the model, we will come up with the rotational matrix that defines the rotation of our drone, like from point A to point B. So this entire mathematics is related to this. Must be noted that the equations and references are mentioned according to our paper, conference paper. So after driving these things, now we come up like in equation number 16, we started the quaternions. In quaternions, you can see the rotation can be restated in terms of rotation vector, where alpha is the angle of the rotation and u is the unit vector. So this can be like q equals to cos alpha 2 plus u sine half alpha. So finally, this entire matrix can be transformed into equation number 17 and 18, as you can see. Moreover, if we see, like we don't only bother on rotation, In this particular paper, we considered like the efficiency, rotor efficiency loss as well, because this is one of the unmodeled dynamic factors. The second thing that we considered was the mass variation, like the mass that is because we consider a drone with a tank in which there is a liquid. So liquid is dropping everywhere, like the liquid is like a disinfectant. We are spraying disinfectant or maybe the pesticides over a particular land, so it's a gradual or smooth variation of mass. Similarly, we consider like a package drop off, like this can be the non-smooth variation mass. Some instant there is a mass and some instant there is no mass. Suddenly the package is dropped. So this is something that is non-smooth variation. So we consider these all things, these three things in our in our model. The third thing is the wind disturbance. So if you can see equation number 37, it comprises the entire relationship between forces and input torque. And apart from that, when we drive this entire mathematics, we use the software that is MATLAB and Simulink. You can see the figure 2, which is basically what we are doing actually is taking the Newton-Euler model in it and driving Newton-Euler into Cottonian. So you can see the inertial measurement unit is sending the data for Euler dynamic models, like it will have the all values with the control inputs, and then you can see the Euler to Cottonian conversions. Afterwards, you can see there's an integrator, and the integrator is actually integrating the all values and providing to Cottonians. After that, you can see the we achieve the Cottonians. So in order to demonstrate the the efficiency, we have done some simulations. So you can see over here, this figure 3 is error of the Euler with respect to wind disturbance. You can see the okay. By the way, the wind disturbance is actually delta D, which is A naught is tap T minus T naught. The T is a current time instant, the time index, and minus T naught is the instant where we provide that the wind disturbance, and A naught is the magnitude. So when we apply this wind disturbance for the Newton-Euler model, the peak value is 10 s to power minus 4 at time instant 10 seconds. You can see like at 10 seconds somewhere over here, you can see the maximum is like is at 30 seconds, sorry. Yeah, so over in from 10 to 30 seconds the time index, and you can see over here the peak value is somehow quoted like 10 s to power 10 minus 4. But if you see like the error rate for Cottonian, it's bit low as compared to the Newton-Euler model. Same case we have done for payload, but smooth variation, like in the case of liquid, where drone is spraying the entire disinfectant on a particular area, or maybe the pesticides over the crops or farms. So you can see the figure 5, over figure 5 you can see the error rate is 13.5 into 10 to the power minus 40. But in the if you see like over here, this is for non-smooth again. In previous we have discussed the Cottonian and all these things. Over here you can see the payload for non-smooth. So non-smooth, again, when we discuss the new Euler, for non-smooth the error is 13.5. It means that in both cases, like smooth or non-smooth, we have the error rate 13.5 into 10 raised to power minus 4. So in non-smooth, you can see like when package drops, it directly come to x-axis without any transition. So when we do the same work for our Cottonian, you can see that error rate now is 88.35 for the smooth variations, and for non-smooth it's like minus 1 into 10 raised to power minus 4. So it's reducing the error rate for Cottonians, and when we talk about the smooth or the non-smooth variations again. Now it's like 15% loss of rotor efficiency. What do you mean by that? Means during our flight mode, we reduces the efficiency of any one rotor, or combinedly we reduce the efficiency of our BLDC, the brushless DC motors, and that is 15% of entire efficiency. So when we reduce that thing, you can see the error rates of in comparison with Cottonian and the Newton Euler. You can see that in Euler we have 13.10⁻⁻⁴, and if we see like in what we say in Cottonian, it's like 1 into 10 to the power -4, and maximum the value is like 8.5 10 to the power -4. So, ladies and gentlemen, if we see like the Cottonian error is evaluated as a norm vector difference between the original and recovered Cottonians. So, using the built-in function of integral square error method, we actually form provided a graph that is in front of you. That is the actually the time index versus the iterations. So the duration of simulation is computed for Euler and Cottonian, and it's highlighted in table number 11. So the time step like delta t, impulse of t have been considered by varying the t max. The simulation time you can see over here is n iteration equals to t max slash this one formula, and these values are illustrated in figure 11. You can see the actually the errors, the number of iterations for Cottonians are less as compared to the Newton Euler. So this is the entire summary of the thing. Like if we see for Newton Euler, in the presence of wind disturbance, the error rates are highlighted here, and the simulation time, that is 6.85 for Euler, and iterations are 8. So again, for the Cottonian approach, if we compare with Newton Euler, it's a bit what we say the robust one as compared to the Euler approach. So the conclusion for this thing is like proposed manuscript, that is our conference paper, is regarding the study of the dynamics for underactuated chord rod with unmodeled dynamic factors, which is the payload and the variation, the rotor efficiency, and wind disturbance. The dynamic behavior of chord rotor is discussed in this entire paper. Moreover, the simulations are done on MATLAB. The perks that we have discussed so far, like with in the presence of unmodeled dynamic vectors, Cottonian approach is quite better. But yeah, the same approach what I studied and mentioned in the conference paper is like Cottonian model is somehow easy and it has more weightage, more perks than the Newton Euler. But the Newton Euler model can be, perform the same performance if we include a hyperbolic function in our Newton dynamic model. This will not create many computational delay, number one. Number two, it will not produce the singularity issue, which will lead to gimbal lock. So many people proposes the hyperbolic function. With hyperbolic function, if you propose, again there is somehow inefficiency in identifying the unmodeled dynamic factor. So for that, people proposes a Haber design observer. So they design observer designs like disturbance observer designs or the extended state estimators. Nowadays it's like active disturbance rejection control design, which are basically working on this particular part. So this entire paper is actually, providing a correlated study between two dynamic models which are proposed widely in this field. The main aim, like what we are expecting in our future, is like to propose a hybrid predictive observer design by taking the Newton Euler model and to check whether the our proposed control design and with the observer can estimate the fast changes in unmodeled dynamic factors, and can we can initiate a tracking of a chord rotor on a specific trajectory within indoor and outdoor environment. I hereby want to acknowledge University Technology Petronas for providing the state-of-the-art approaches, state-of-the-art research facilities, and apart from that, I'm really grateful to the Yayasan University Technology Petronas, YUTP funding, The grant number is 015CL0316. I'm really grateful that under this grant funding, I'm pursuing my PhD studies in same area. I would like to thank my mentors who are the co-author of this paper, Dr. Saiful Azrin BM Sulkifli. He is my co-supervisor, and the main supervisor is Dr. Vijant Sagyana Srivardhan, Department of Electrical and Electronic Engineering, University Technology, Patna. So these are the references, ladies and gentlemen. These are my contact details. You can WhatsApp me, you can email me, and my LinkedIn profile is over there. And I'll be really delighted and overwhelmed for any research collaboration together. So thank you so much. By the way, this building is the Chancellor Complex, beautiful Chancellor Complex of our University Technology Patronage. Thank you.